Hi everyone, thanks for joining us today for our Lead and Copper Control with Phosphates webinar. I'm Liz Mueller with Carus Corporation and I will be our moderator today. We have two speakers, Darren Scott with Carus Corporation and Mr. Mike Kosterman with Racine Water Utility. We are recording the webinar today and we usually have that available in about 48 hours after the webinar. We put that on our YouTube page and our website, and we will also email out the link to the recording to all of the attendees. Here's a look at some upcoming webinars that we have. We have permanganate for landfill leachate odor control, and that's going to be in November with Mr. John Bull. And then we also have Carus CR tablets solving hydrogen sulfide odor problems. That will be sometime in December with Mr. John Bull. So keep an eye on our website as we firm up those dates and times. We'll have those posted. And then also we post them on our website under our water tab. Webinars is where you can find the list. And on the right-hand side is a link to all of our previously recorded webinars as well. How to find us. So here's some information on how to find Carus, our website, our general sales and marketing email address, my email address, and then we are active on the following social media platforms. So follow our Carus Corporation page on LinkedIn, YouTube, Facebook, or Twitter. And here we're going to launch our first poll. So it's where are you located? And that should be live now, so go ahead and fill that in where you're located or based. We'll give it about 30 seconds here, and then we will close the poll. All right, great. So it looks like most of our participants are located in North America. So welcome everyone to our poll, or to our webinar. With that, I'm going to introduce our speakers today. So Mr. Darren Scott will start the presentation, and then we will turn it over to Mr. Mike Kosterman, who will go through a case study. So Darren Scott works for Carus Corporation. The first 2 years at Carus were spent as a quality control chemist, and the last 16 years as the technical service manager. As a technical service manager, Darren conducts laboratory testing and product demonstrations for Carus Corporation, municipal, industrial, and environmental customers and prospective new customers. He also conducts technical training and safety presentation and recommends safe chemical handling and dosing systems. He's a graduate from Illinois Wesleyan University in Bloomington, Illinois, with a BS degree in chemistry, ACS certified. Mr. Scott is a member of AWWA, Water Environment Federation, and the American Chemical Society. Also, our second speaker is Mr. Mike Kosterman. Mike Kosterman is the water plant superintendent at Racine Water Utility. Mike has spent the last 22 years with the city of Racine. Prior to his current position, Mike worked for Central Lake County Joint Action Water Agency as a laboratory supervisor. Mike is a member of American Water Works Association, AWWA, and West Shore Water Producers Association, where he was a past president.
So we'll begin today talking slightly about a Carus introduction of where we're located, and then we'll go into the US EPA lead and copper rule, some factors that affect corrosion and prevention, a brief history of phosphates, a selection of what phosphates you would pick, what benefits you would have, and then we'll finish with Mike Kosterman talking about Racine Water Utilities, lead and copper. Carus Corporation was founded in 1915. Our headquarters are in Peru, Illinois, and we have two manufacturing facilities here in the U.S., one in LaSalle, Illinois, and one in Belmont, North Carolina. We sell internationally, and we have distribution organizations. Our primary focus is on drinking water, wastewater, air purification, soil, and groundwater remediation, and we hold several certifications for our products. We are a responsible care company. We also have NSF certification, which includes ISO certification as well for our plant. We have sales teams both here in the US and then in Europe and in Asia, with our headquarters located here, warehouse facilities in Europe, and then technical service here in the US that works worldwide with our customers. So the rule that governs what we're going to talk about today is the US EPA lead and copper rule that was put into effect on June 7th of 1991. What it said at that time was what the current action levels for lead and copper would be. At the time, the lead action level was 0.015 milligrams per liter, or usually you'll hear it referred to as 15 parts per billion. And for copper, the action level was 1.3 milligrams per liter. That original document actually set goals as well and said the maximum contaminant level goals for those two compounds. For lead, it was 0, and copper was 1.3. So in the case of copper, the action level and the goal were the same, but with lead, it said that the action level was 15 parts per billion, which your goal would be 0. With the recent news with Flint in the last 2 years in the media, you've heard many people refer to that there's no acceptable level of lead. Well, they're using this old document and the goal and saying that the goal was always supposed to be 0 to say that's why none would be acceptable in the field. The reason lead and copper rule was put into face was because of the issues that lead causes in the delays of physical and mental development of children. Can also cause kidney problems and high blood pressure in adults. Copper causes stomach, liver, and kidney problems. So there was reasons behind putting lead and copper rule into effect. The lead and copper rule is different from most regulations because it's an action level, which is different than a maximum contaminant level. In the case of an MCL, you can have no sample that's above the limit. In the case of an action level, you only need 90% of your samples in the distribution system to comply with the regulation. You're allowed to have 10% that are above the regulation. So the easiest way when you're doing your lead and copper rule numbers is to take all those samples, put them in a spreadsheet, and sort them from highest to lowest, and go 9/10 of the way up the list, and that's what your action level is, and that determines if you're in compliance. The monitoring for the lead and copper rule is based on the size of the distribution system and the high-risk sites that you have out in the distribution system. High-risk sites would be places where you know you have lead service lines or you have copper plumbing in the consumer's home that has lead solder. The original frequency is every 6 months for additional monitoring of the lead and copper rule. If you meet that regulation and the action level, systems consistently meeting it can reduce the monitoring to once a year. If you continue to meet the regulation, you will then cut your number of samples that you need to test for in half. And then finally, as you continue to be in compliance with the regulation, it goes to once every 3 years and half the number of samples that you need to pull in the system. So there are benefits of getting the lead and copper in your system under control because it's less testing and half the number of samples. The lead and copper rule is different than most regulations because it requires a sampling of a first draw. So this means the sample is collected at the consumer's home, and it should be 1 liter of water from a cold water tap that has not been used for at least 6 hours in the consumer's home. The current regulation sets no upper limit on stagnation time. Technically, most water plants will tell their consumers they'd love that tap sample to be picked between 6 and 12 hours that it's sat stagnant, but there is technically no upper limit on it. In 2016, after the issues with Flint, the US EPA sent out a recommendation update and recommended several things that utilities must not do when they work with customers. At that time, they recommended that you not recommend a pre-flush to the consumer, which means the night before the sample is pulled, you should not recommend that the consumer flush their water line for 5 to 10 minutes prior to shutting it off before starting the test. That recommendation also said that you should give the consumer wide mouth sample bottles so that they can open the faucet fully to collect that water sample. The reason for doing that is the higher velocity, if you open the sample tap up completely, you would get particulate lead could possibly flush out into the sample, and the US EPA wants to collect that data to see if that makes it into the sample. And then finally, they recommend that you don't remove the faucet aerator from the consumer's tap before they pull that sample. You want the sample acting like they normally would collect their sample when they wake up in the morning and drink from the kitchen or the bathroom sink. And those were the recommendations. If you have a violation of the lead and copper rule, after the exceedance occurs, you need to do a distribution of public education, so notifying the public that you've had that exceedance. What happens is you go back to increased monitoring of consumer taps. So you go back to monitoring every 6 months and the full number of samples. In addition, you're required to develop and submit a corrosion control plan to your state regulatory agency of how you're going to get back into compliance. That corrosion control plan can include how you would adjust the pH, the alkalinity, the hardness, or if you're going to add a corrosion inhibitor or change the dosage on the corrosion inhibitor. The lead and copper rule also lays out that you can choose an alternate way of compliance of doing lead service line replacement rather than doing a corrosion control plan. If you choose the path of lead service line replacement, the regulation states that you must replace at least 7% of the lead service lines per year until you have them all removed from your system as a path forward. All these things will be up for debate when the new US EPA lead and copper rule comes out. It's tentatively set to be released in early 2018. So because of the lead and copper rule, there's lots of issues with corrosion out there in the distribution system for water plants. Some ways to determine if you have corrosion in your distribution system is to look and see if any of these things on this list are issues that you have in your system. Do you have tuberculation deposits? When you cut out pipe or you work on main breaks out in the distribution system, do you see a lot of scale and tuberculation on the inside of the pipe? Are you seeing an increased cost to pumping water through your pipe? As that pipe gets restricted with scale and tuberculation, it costs you more in energy to pump the same amount of water through the pipe when that scale and tuberculation builds up. Do you have an increased chlorine demand in your distribution system? You're feeding your chlorine at the plant. Do you have to boost it out in the distribution system to maintain that residual in the system? Do you have places where the residual drops off frequently? Those are all good hallmarks that you might have issues with corrosion in that part of the distribution system. Have you had any issues with bacterial regrowth or hits with bacteria out in the distribution system? Bacteria can be a major form of causing corrosion out there in the distribution system. Do you have a lot of issues with dirty water, red water complaints in the distribution system, and you're sending your team out to flush the fire hydrants frequently? And when they do that flushing, do they have to flush the fire hydrants for 5 minutes, 10 minutes, 30 minutes? The longer that you have to flush the fire hydrant until you get clean water is a good hallmark that you have a lot of corrosion going on out in your distribution system. Obviously, leaks in main breaks would tell you you have severe issues with corrosion in your distribution system because now the pipe is actually corroded so much that it's caused a crack and you're leaking water out into the ground, and you have to do replacement of those. Overall, though, all these things on this list lead to a decay of water quality that causes the water that leaves your plant, which is crystal clear and tastes great, by the time it gets to the consumer, it's picked up color, it's picked up taste from that tuberculation and scale, and the customer is calling you to complain that the water doesn't meet their expectations. And customers are always going to let you know when they turn their tap on and the water is discolored or tastes funny. They're going to find somebody to call, whether it's somebody at the water plant or somebody at City Hall, to complain about it. So when we talk about corrosion, these are kind of the standard factors that we would look at. pH is always the number one that you look at, that you measure at a water plant, and one of the things we look at. We know that low pHs below 7 are acidic, and they will increase the amount of corrosion that you have in your system. As you increase pH, that typically protects the system, and so pHs in the 7 to 8 range, or going higher from 8 to 9, tend to be protecting for the distribution system. In addition to pH, alkalinity is another important factor to measure. Alkalinity helps you form the calcium carbonate coating out in the distribution system, and it also acts as a buffering agent for your water, which helps you keep your pH at a stable level throughout the distribution system. Systems that have low alkalinity typically can see pH swings in the distribution system, where water leaving the plant will be at 1 pH, and depending on what's going on in the distribution system, it'll either swing higher or lower depending on what type of corrosion byproducts they have in the system. Some other products you'll look at is DO, dissolved oxygen, which would increase the rate of corrosion in your distribution system. Chlorine residual, or nowadays you also see chloramine residual. Chlorine residual specifically increases metallic corrosion in the system, and chloramine residual is less effective at removing biofilms from a distribution system versus free chlorine. So there can be differences in how those work in the distribution system. Finally, one of the last things that many states are adding to their corrosion control chemistry is DIC, which stands for dissolved inorganic carbonate. It's a measure of a lot of different factors in your distribution system, and a high DIC increases how conductive your water is and would actively prevent, if you have a high DCI, a high DIC would prevent corrosion control techniques. What that means is you might have to feed more phosphate or have a higher pH or a higher alkalinity to try to combat that high DIC interference with your corrosion prevention. When we talk about methods to reduce corrosion, there's some standard techniques that most water plants will take into account. pH adjustment generally is the first one that most plants will consider because it's one of the easiest chemistries to add. Next would be passivation techniques, which would be adding carbonate or calcium adjustment to the water. So this would increase the amount of calcium carbonate in the water or the alkalinity in the water to help you have that buffering effect and help lay down a calcium carbonate scale. Finally, you can do corrosion inhibitors, which would be phosphates or silicates that can lay down a phosphate or silicate coating on the inside of the pipe. There are some other techniques you can take into consideration. One would be a reduction of your DIC, which would be achieved through either aeration of your raw water or through a process like lime softening or ion exchange before you send the water out the door. Finally, you can do some physical protection of tanks and piping out in your distribution system. This type of corrosion protection would only protect that piece of equipment, but where you would see these is in water towers and water tanks, where they do either electrodes to protect the tank or they'll do coatings to protect the tank from corrosion issues, and that's to protect one part of the distribution system. Generally, phosphates in water treatment are used for two main applications. They're used for corrosion control, which would be lead and copper, and also red water complaints. And they're also used for sequestration, which would be color control, scale control. The last time that AWRF did a study on this was in 2001, and 56% of all water utilities in the US use some type of phosphate-based corrosion control / sequestration. At that time, they said roughly $200 million was spent a year on phosphate products, but it resulted in a $4 billion savings for these water plants, which was a 20-fold return on investment. How AWRF came about those numbers was they had the cost of the phosphate products, but to get the savings, they added up all the things that a water plant would normally do when responding to a customer complaint. This could be going out and collecting water samples, the additional testing they would do, the other treatment chemicals that they would do in the plant. Did they have water mains and leaks? Did they do more flushing? All those things have a cost associated with them, and they added those up, and that's how they came to the $4 billion in savings. At the time of the study, and even today, there's a wide range of costs for phosphate products in the market. Depending on what type of phosphate you're using, the cost can be anywhere from 30 cents to $2 a pound, or 1 cent to 10 cents per 1,000 gallons of water treated. One of the things that we get asked frequently here at Carus Corporation, especially for any customer that has not used phosphate in the past, is we're adding a new chemical to the drinking water treatment. Is this going to be harmful to consumers? Well, phosphates are something that we come into contact with every day. They're a food additive. They're used as a leavening agent in donuts and in bread. They're a dairy emulsifier, so they're in the cheese that we eat. And they're in the can of soda that you drink, beverages, at less than 1% phosphoric acid. So we come in contact them with levels anywhere from 1,000 ppm to 10,000 ppm on a daily basis. We also find phosphates in toothpaste as plaque inhibitors and whitening agents. They're used in some drug manufacture. By far the largest application is fertilizers for farm fields and for the grass in your yard. And then finally, you do still see some phosphates in cleaners and detergents.
All right, great. So we're going to pause here real quick and take one more poll question. The poll question is, are you currently using phosphates? So we'll give you guys about 30 seconds to go ahead and answer the question. All right, great. So the results are in. It's about 52% are currently using phosphates. Thanks everybody for answering. We will turn it back to Darren.
So when we talk about these phosphate classes, there's two very distinct classes. Orthophosphate, which contains one PO4 unit, and polyphosphate, which is also sometimes referred to as condensed phosphate, which contains several PO4 units chained together. So orthophosphate, like I said, is just one PO4 unit for itself. Polyphosphate can contain 2 or more PO4 units in a straight chain, like you see in the picture, or it can be a metaphosphate, which contains 3 or more PO4 units in a ring structure. The different types of polyphosphates allow it to do different things versus sequestering of iron and manganese versus threshold treatment of calcium carbonate. There's been a lot of research done over the years on the corrosion control mechanisms involved with phosphates. What we do know is that phosphates form films over pipes or metals out there in the distribution system. They are anodic film formers. So the orthophosphate is slightly negatively charged and forms a film on the inside of the pipe by attaching to the metal. Polyphosphates can also act as a cathodic inhibitor, and they provide a barrier between the metal pipe surface and oxygen to prevent that interaction of the oxygen with the metal pipe surface. The research has shown that these thin films are very insoluble phosphate salts, and we are still doing research today on how these films form, how long do they stay active, and what are good levels of phosphate to feed in the distribution system. The orthophosphate research that you can find out there today talks about orthophosphate precipitating with the 2+ valence metals. So that would be the calcium, the magnesium, the lead and copper pipe, and the iron and manganese you would have in your distribution system. Michael Schock did a lot of the original work on the formation of the insoluble film out in the distribution system. What we know is that we bond directly with the pipe wall itself or with some of the soluble ions in the drinking water itself. As little as 1/2 part to 1 milligram per liter as orthophosphate reduces the amount of iron that releases from cast iron pipes by 2/3. But overall, the orthophosphate research shows that they reduce corrosion in the distribution system and would lower your lead and copper numbers and red water complaints. A typical optimal orthophosphate dose would start at least 1/2 milligram per liter as orthophosphate to reduce lead and copper solubility in a pH range of 7 to 9. The current EPA guidance manual talks about feeding up to 3 milligrams per liter. Why that is because once you get above 3 milligrams per liter as orthophosphate in the distribution system, it yields little change in the numbers that you would see and the reduction in lead and copper that you would see in the distribution system. Typically, most water quality plants will maintain a level anywhere from 1/2 part to 1 milligram per liter if they're just feeding an orthophosphate product to the distribution system. That's important to keep in mind because a lot of customers are feeding blended phosphates which contain ortho and poly, and that 1 milligram per liter would only be normal if you're just feeding orthophosphate with no polyphosphate present. Polyphosphates are known as the sequestering in the distribution system. They are the bonding of that polyphosphate to the metals in your water. What they do is they prevent chlorine, which also acts as an oxidizing agent in addition to being your disinfectant in your distribution system. Typically what happens is chlorine will oxidize the iron and manganese in your water and precipitate it out of solution. If you have iron, the water will become rusty orange as it gets oxidized, and if you have manganese in your water, it will become black to brown depending on the concentration. The other thing that polyphosphates do is called threshold treatment. They prevent the calcium and bicarbonate ions from pairing together and forming calcium carbonate scale. What happens is you'll retard that crystal growth, and you won't form the scale that you see in the pipe on the right-hand side of the picture. Why do we want to prevent that? Obviously, that pipe is severely restricted with that much calcium carbonate scale. For corrosion control, you would love a thin scale of calcium carbonate, but you don't want it to keep building on itself to the point where it actually restricts the pipe. So when we talk about color control and the use of polyphosphates for sequestration, typically what we would say is when you're using it for iron and manganese sequestration, if you're above the US EPA secondary maximum contaminant levels. What those secondary maximum contaminant levels are aesthetics. They're not health effects. So water that contains iron above 0.3 milligrams per liter and manganese above 0.05 will cause staining of fixtures and laundry in the consumer's home. If you're above those levels in the water that goes out the door to the consumer, you would use a polyphosphate to sequester them so they don't precipitate out and cause those color issues in the distribution system. Typically, the place you see the most sequestering used and polyphosphates used is in groundwater plants where they're doing no oxidation and no filtration before they send the water out the door to the consumer. In place of that oxidation and filtration, they use the polyphosphate to sequester the mineral content. The other major use is calcium carbonate scale control. Anytime you have a high hardness water, you have a chance for having calcium carbonate scale. As you increase your pH, you increase the likelihood that calcium carbonate scaling will increase in the distribution system. Anywhere from a range of 150 to 400 milligrams per liter of calcium carbonate can cause scaling issues like you see in the picture, and polyphosphates will help prevent that scaling from getting that bad. Just like with orthophosphate, there's been a lot of polyphosphate research done over the years. That research involves as simple as the sequestering of the metals is dependent on what type of water chemistry you have. So looking at the pH of your water, what other things are in the water in addition to the iron and manganese you're trying to sequester. We know that polyphosphate reduces the apparent color and turbidity in iron colloids, so iron is one of the things that's very easy to sequester in the distribution system. There has been additional research that shows polyphosphates help improve disinfection in the distribution system in combination with chlorine. What happens is the polyphosphate helps break up the biofilm in the distribution system, and now your chlorine can more effectively remove the biofilm. The paper by Lee Cavalier talks about a 1,000-fold decrease in biofilm counts from the combination of polyphosphate with free chlorine versus just free chlorine by itself. One of the last things we know is that polyphosphates do have a shelf life, and they revert to ortho over time. What this means is typically a polyphosphate product has a shelf life of 6 months to 1 year before you start to lose most of the polyphosphate to orthophosphate. So you'll want to take that into consideration when sizing the tanks in your plant for how much product you want to store and how much you're going to use. Typically, optimal polyphosphate dosing is going to be based on how much iron, manganese, and calcium carbonate hardness you have in your water. Typical dosages anywhere from a half a part to 4 milligrams per liter, and the dose is going to really depend on how much stuff you have to sequester. So the combination of poly and ortho blended phosphates became very popular in the 1990s when the lead and copper rule came about. A lot of plants, especially groundwater plants, had to do both sequestration and corrosion control at the same time. So they chose products that combined both poly and orthophosphate to give them both of those benefits at the same time. They would provide the corrosion control they needed to meet the lead and copper rule, as well as sequestering the iron, manganese, and calcium carbonate in the distribution system. The doses for an ortho-poly blend are a combination of the two dosages you saw earlier. Typically, you'll see anywhere from a 1/4 part to 1.5 parts as orthophosphate, and then anywhere from a half a part to 4 milligrams per liter as total phosphate. The difference between the total number and the ortho number is how much polyphosphate you would have in the system. Your dose is going to be dependent on your water quality for your situation and what type of blend are you using. So typically higher dosages would be if you're sequestering in the distribution system, and if you're just looking at corrosion control, then you would typically be on the lower end of that scale for dosages. Which choice of phosphate to use can be as critical as dosing. Some of the things you want to consider when picking a phosphate product for your specific water quality is what is the water quality leaving the plant going out the door, and then what does the water quality do as it goes throughout the distribution system. Then what types of problems are you having in the distribution system? Are you mainly having calcium carbonate scaling issues? Are you having issues with dirty water, red water complaints in the distribution system? And then finally, what are the treatment goals that you're trying to achieve with the phosphate product? Are you mainly looking at lead and copper control? Are you looking at lead and copper control plus sequestration? What are the goals that you're trying to achieve with the product you pick? Typically, the first things you're going to want to determine are what is the hardness of the water, what is the soluble iron and manganese after filtration, if you have filtration, going out the door to the consumer, and keep in mind that there are the secondary maximum contaminant levels for iron and manganese. Do you have any background orthophosphate? If you're a groundwater source, sometimes you will find that in your source water. You need to take that into account. And then what is the pH of your water going out the door to the distribution system? For a blended phosphate of ortho and poly, pH 6 to 9 will work, but it's optimal between 7 to 8. If you're using a zinc orthophosphate, a pH of 7 to 3.3 to 7.8 is optimal. So those are some of the things you need to take into account. In general terms, kind of give you an idea of where you would start with a phosphate product. If you have no iron and manganese, and you have a corrosive water which has a low hardness, low alkalinity, then you would be in the product line of orthophosphates, which would be the Carus 3000 or Carus 4000 series. If you have a lot of iron and manganese, so say 2 parts of iron or 0.3 milligrams per liter of manganese, or you have a very high hardness, 200, 300, 400 milligrams per liter, then you'd be in a product that's straight polyphosphate, the Carus 1000 series. For most water qualities, you'll fall in the middle between those two ends of the spectrum, and you'll use a blended phosphate, which would be the Aquamag or the Carus 8000 series. And the blend ratio will change to more polyphosphate the more stuff you have to sequester in your water. Whereas if you're more focused on lead and copper control, you'll have a higher orthophosphate versus polyphosphate ratio. When we talk about phosphate injection applications, we typically inject phosphate solution with a corporation stop in the main prior to chlorination. This is especially important if you're using the phosphate for sequestering of iron or manganese. You need to get the phosphate in first to sequester the iron and manganese before you add the chlorine, because chlorine will oxidize it and precipitate it out. Once the iron and manganese is precipitated, you can't resequester it back into solution, and you'd have to filter those solids out. Typically, phosphate products are fed neat directly from the container. You don't need to add carry water unless you want to. A good rule of thumb is that for every inch diameter of the pipe that you're going to inject the phosphate in, you would like a distance of 1 foot between the two contact points, with phosphate being first. If you had a static mixer, you can shorten that distance, but phosphate blends in readily with the water. You can use just about any type of pipe or pump with phosphate, whether it be peristaltic or a membrane chemical feed pump. And we have customers today that flow pace or SCADA control their pump based on their flow rate. Once you start feeding the phosphate, you can monitor how the phosphate is working in your system by measuring the orthophosphate levels in your distribution system. The US EPA has an approved method that you can use, and it measures orthophosphate residual in milligrams per liter. So while you're collecting those samples for chlorine in your system, you can split the sample and use a portion of it for the orthophosphate test. You add the powder pillow, you let it wait for 2 minutes, and the darker the blue the sample takes, the higher the orthophosphate content you'll have in your system. This is a way for you to measure what type of orthophosphate you're feeding and how much is making it out into your distribution system, to give you an idea if the numbers match what you're feeding and what you're seeing in your distribution system. So in summary, phosphate use in the US is pretty extensive, anywhere from very small systems, groundwater plants, to very large municipalities like the city of Chicago, Los Angeles, and Miami. Generally, the benefits are worth the cost. Obviously, if you're failing the lead and copper rule, they can help you get back into compliance with that regulation. They can also help have cleaner, clearer water for sequestration out in the distribution system. They can reduce the amount of time you have to flush in the distribution system, and they can cause reduced disinfectant demand in the distribution system. But overall, the use of phosphates leads to better water quality in the system.
All right, we're going to take our last poll here before we turn it over to Mike. How did you hear about our webinar? All right, we'll give it a couple more seconds. Looks like most people are receiving our email blast from Carus, which is great. If you're on this call and you're not, but you'd like to receive those, please let me know. We'll get you added. All right, we'll go ahead and close this and turn it over to Mike from here.
Okay, can everybody hear me okay?
Yep, sounds great.
And hopefully you can see my screen.
We can.
We'll get underway here. Again, I'm Mike Costner with Racine Water Utility, and give you a little bit of background about Racine Water. Racine is a typical upper Midwest industrial town. Started in 1860, but actually first started using Lake Michigan water back in 1886. This is a picture of the social event back then, with no TVs, radios, or our cell phones in our hands. This is what people did. They looked at fire flow tests. That was entertainment back then in 1886. For all of you not as familiar with where Racine is located, we're right on Lake Michigan, shoreline Lake Michigan, about 20 miles south of Milwaukee. We're the third largest surface water plant in the state of Wisconsin. Milwaukee has the two largest plants. Our conventional plant is rated at 60 million gallons per day. We have ultrafilter membrane following our conventional plant rated at 50 million gallons per day. We serve a population of anywhere between 100 to 110,000 people. We started out with approximately 14,000 lead service lines, probably about 2,000 to 3,000 less than that right now. We stopped using lead service lines in around 1940, right before World War II. And historically, we've been performing partial lead service line replacements as we do water main projects. Again, that's kind of a no-no. Obviously, now with what's done in research and the potential for elevated lead levels, we do have we've received some grant money the last couple of years from the Wisconsin Department of Natural Resources to help our private citizens to replace their side of the lead service line, and we're progressing with that quite well. So where we can, we do full lead line service replacement. I started the water industry back in 1984, and looking at lead and copper, unfortunately, about 32 years of my experience have been dealing with lead and copper rule in some fashion. It was first promulgated in 1986, and when it was, the previous superintendent here and I conducted a lot of research. We trained a number of our employees that had lead service lines, and we did some pH adjustments and alkalinity adjustments like Darren has suggested. Took first draw water samples at about 12 individual homes over the course of each quarter of the year, trying to account for temperature effects in that. Again, we did that from 87 to 91. 92, monitoring began across the country. And again, since we were a large utility, we were mandated to do corrosion treatments, which we did beginning of 1993. It took us until 1996 where we deemed that we had met the action level and had achieved corrosion compliance. And we sailed along in compliance, barely in compliance, I'll add, until 2004. And we exceeded the lead action level, unfortunately, which of course initiated a lot of things like public education, studying what we're going to do. So we kind of remained out of compliance for 06 and 07. 08, we made a treatment change, which I'll talk about later. We changed our main coagulant, and we came back into compliance in 08. We changed our corrosion inhibitor, the formulation, in 09, further improving our lead and copper numbers. And we continued through 2011, meeting all the action limits with flying colors, basically. And then 2014 hit, and there's some theories as to what happened, which I'll again talk about a little bit later in the talk. We were out of compliance, again, which initiated public education, of course, and initiated the necessity to start removing or replacing lead service lines, which again I'll explain a little bit further. 2015, we did a lot of extensive lead testing. We also came back into compliance in 2015, and for the last 2 years, 16 and 17, our numbers have been excellent as far as our 90th percentiles for lead and copper. And in 2018, like everybody else in the country, we're waiting for the EPA to come out with the revised lead and copper rule. And of course, we're kind of dreading what they're going to require all its utilities to do, or the changes that may be made. So, again, if you look at this graph, you'll see that from 92 when we started testing until 2004 when we had our upswing in the 90th percentiles, even during that time period in the early and mid 90s, our 90th percentile was still relatively high. We're skating along at 13, 14, 11, 12 in that area. So we're right on the cusp of going out of compliance. And unfortunately, in 2014, we did. We got a waiver for sampling in 2015, try to get our house in order. We made a 06, we changed our chemical supplier and started using a Carus product, a 40-60 blend, 40 Ortho, 60 poly, and carried on that way through a few years, again, with no success in reducing ourselves back down below the 15 part per billion action level, unfortunately. During that time period, we were required to do an investigation. We did loop studies looking at different chemical formulations as to what would be the most effective. We were out in the system doing surveys on our homes where we do our monitoring, looking at stray voltage, grounding effects. Obviously, most of the homes in an older city like us, they have all the appliances grounded to the water pipes, which is obviously not best practice. And we found very little correlation between stray currents and grounding effects as to what the lead and copper would be. So again, we tried, but we didn't really see any strong correlation. And of course, we had to produce a report submitted to our DNR to give recommendations as to what we were going to be doing in the upcoming future to get ourselves back into compliance. Again, very, very involved work at this point. A lot of man hours put in. But in 2008, again, we're sampling twice a year, a minimum of 100 samples in each half of the year. Our 90th percentile dropped down to 11, which is one of the better numbers that we have seen. So what happened in 2008? Well, we made a coagulant change. We had been using iron coagulants, ferric chloride and then ferric sulfate from the years 1987 through 2008. We decided that we wanted to look at an alternative product, did jar testing with a chemical supplier, got DNR approval to do a plant trial, and we switched from ferric sulfate to polyluminum chloride. And the goal, our intention for making the switch has nothing to do with lead and copper. It was strictly resulting from the fact that our membrane plant, the fouling that was occurring on the membranes was due to iron carryover from the conventional treatment process, clogging the pores of the ultrafilters. Again, there is, even though it's very low levels of iron, basically undetectable, there were still small particles of iron precipitate that you couldn't see that were clogging the pores on the membrane. So again, the idea here was to increase the efficiency of our membrane plant. Fortunately for us, we found out that the switch over from the iron salts to polyluminum chloride provided a number of other benefits in our treatment process and effects on water quality. And one of the things we noticed was the effect of pH. Again, historically, Racine had been an alum plant. We switched in 1987 from an alum to an iron salt. Iron salts depress pH more, and you can see from this graph and the how far this graph goes back to 1997. But before then, too, from 87, our pH of our finished water leaving into the distribution system was around 7.4, 7.5. And with a switchover, we immediately noticed a rise in pH. And typically now our pH, our finished water pH averages about 7.7, which obviously, as Darren explained, higher pH equals less corrosion. So there was a big benefit right there. Again, this is all happening in 2008. The other thing that happens when you treat the water from Lake Michigan, the alkalinity of Lake Michigan is about 110 parts per million. And through the treatment process, we would typically depress that pH, or excuse me, the alkalinity by about 10 parts per million, especially when we were using the iron salts. When we switched over to the polyluminum chloride, less alkalinity depression, so our alkalinity leaving the plant in the water, it was raised by about 5 parts per million. Again, so this switch over in coagulant, not even looking at really water quality, we want to reduce the fouling rates in our membrane plant, resulting in a less corrosive water. So we like to believe what the evidence shows us that even that slight change in pH and slight change in alkalinity brought us back in compliance back down. It was just enough to force the phosphates to work better. Looking at 2009, you can see our 90th percentile now dropped to 6.7, further improvement in the lead levels in our first draw sampling program. And what happened in 2009 is we, after our studies were completed, submitted to the Wisconsin Department of Natural Resources and accepted, we switched over to a blend of 8600, as Jaron was explaining, their mid-level product, 70% ortho, 30% poly. And again, you can see looking at the numbers previous years, going back in the 90s, we were carrying an average ortho level of about 0.25 parts per million. In 06, when we changed to the 40-60 blend, you can see our orthophosphate obviously went up to about 0.4 parts per million. And then with the switch over in 2009, we're looking at obviously a target level of 0.7 ppm, and that's basically where we hit. So again, we increased, basically almost tripled the orthophosphate level that we're carrying in our finished water out in the distribution system, which accounts for a lot of the improvement. Again, looking at the graph from 2010 to 2011, again, we have good numbers here. We're very low, and we were very pleased with what was going on. We thought we had a real good handle on the lead and copper rule, and finally we felt we had some breathing room where we were not going to have further problems. But then 2014 hit, and our 90th percentile zoomed up to 25 parts per billion, which obviously triggered a lot of head shaking here. And what are we going to do? What happened? In looking at our sampling program, I believe we sampled about 70 homes that particular year. We had not sampled since 2011 because we were on a reduced monitoring schedule. We found out two of our long-time samplers had decided that instead of sampling from the kitchen faucet where they normally had, one of them decided to sample from the laundry tubs, which they never used. Another sampler decided that after coming home from vacation, she decided to take the water out of the bathtub because she was just curious to see what would happen. So obviously, if those two people had sampled where they normally have, we probably would not have gone out of compliance. We took the 7 or 8 sample sites that were over the action level, went back and resampled all of them except one in December of 2014, and all of those samples came back down below the action level. So what had happened in the summertime sampling and what changed at the end of the year kind of remains to be unknown, but that particular year, there's this theory going around in the state of Wisconsin. A number of utilities failed in 2014. There's a theory going around. We had a particularly bad winter, very cold, very long. Started in early December of 2013 and continued all the way into April of 2014. We had frost in the ground below 7 feet. Obviously, their surface lines are 6 feet down. They're surrounded by frozen dirt, and there's some theory that maybe these cold temperatures reaching down to the surface lines into the water mains changed the crystalline nature of the film that was built up, and we started releasing lead. That's just a theory. I don't know if there's any proof that's ever been found that happened. But again, the other thing that happened in 2014, we actually had a copper for the first time in the history of our monitoring program. We had a copper level that exceeded the action limit. That's the first and only time we ever had a copper exceedance. So of course, when you're out of compliance with the lead and copper rule, especially on the lead side, things that kick in, again, are public education, which again, we had to provide brochures to our customers, take out advertisings in the local media, radio, television, newspapers, and then you have to start replacing 7% of your lead service lines. Now, if you're talking about 10,000 lead service lines in the city of Racine, that means a minimum of 700 samples we're going to have to replace that first year. In the lead and copper rule, there is a ability to, instead of actually doing full lead line service replacement, you can test out of it by taking lead service line samples and seeing where you stand on there. So that's what we did, because basically the cost of doing the lead service line replacement would have exceeded $3 million in 2015, which we did not have in our budget. And more importantly, it would have been impossible to replace 700 lead service lines by September 30th of 2015 as required in the lead and copper rule or the DNR regulations, which are the same. So we decided to test out the program. We got a bunch of volunteers, actually 720 homes participated in a voluntary program to test for lead in the service line, not first draw, lead service line. Sample kits and detailed instruction were given to volunteers. The sampling occurred basically in the same time period that we had to do our compliance monitoring, and it took basically all summer long to complete this. And we were pleasantly surprised to find out that out of the 720 samples, 6.4 exceeded the action level, or 46, and the action level would have been 11 parts per million on that lead service line. Worst case scenario, what we were trying to determine, our action level is 11 parts per billion, which we were, again, very pleased. Again, one of the things, and again, looking at all the lead sampling we did that year, we processed nearly 1,000 samples for lead and copper in 2015. Again, we did hire someone else. We couldn't do that internally. We didn't have the manpower to do this program, so we did contract a lot of this work out. But one of the things we did learn is that since we knew we had sampling errors out there where people were not following sampling instructions, we looked in detail at our instructions to our samplers, our volunteers, and came up with this form where the sampler actually completes the survey. So if there's any, in answering the questions, if there's any doubt that we're not sure about this water, we will not submit that sample, and we will go back to that person and have them resample. The other thing that we did here in the utility here is that anybody that participated voluntarily in the program would get a $25 rebate on their water bill, and that really helped out a lot for people actually doing this work for us, because again, it's impossible for a utility to get out at 6 o'clock in the morning and go to these homes and sample everybody's home. We really have to rely on the homeowner to properly take the sample and participate in the program. So what we did here is we also gave them a link to a YouTube video where they showed proper sampling technique. Again, we really made a strong effort in trying to re-educate our volunteers in proper sampling technique. And basically, we're just improving our quality control. So in 2015, after our failure in 2014, we did not change any of the water chemistry. We did not adjust chemical feed rates for our inhibitor at all. We just tried to re-educate our samplers to do the proper sampling technique. And if you look at our numbers right now, from 2015, both halves of the year, 16 and 17, we have excellent numbers, consistently good, excellent numbers. Again, we feel that we're back in control of the situation. At least that's the way we feel. I'm knocking on wood right now. And we also looked at our lead and copper numbers a little bit differently. Also, looking at the average lead values, basically the spikes you see here back in 2004 and 2014 were due to the fact that a couple of samples that I mentioned before, they were real high, which really throws off the average. But again, if you look at the trend line over the time period, you can see the last, starting in 2010, when we had made full changes, and then of course 15 through 17 here, our average number for our lead is really down low. And again, looking at a median value, again, this shows significantly that we've really made improvements in the overall lead numbers in our finished water and distribution water out in the system, where half the values are above this number and half of them are below. So again, looking at this, we're at 1.3, 1.6 in that range. So we feel, again, looking at these numbers, again, it's just further proof that the lead numbers have come down significantly due to what we've done here in our treatment process. Copper numbers, whoops, I'm sorry, go back here. Figure, too fast. Looking at copper again, we never really had some issues, but again, looking back at 06, 07, that time period, the 90th percent of the copper numbers were a bit higher than what we are experiencing right now. So we're right around that 300 part per billion level at the 90th percentile again. So and again, I did not include graphs for medium and average values, but they basically show the same thing for copper. We've never really had a copper issue here in Racine so far with the lead copper rule. So points of emphasis, our average, medium, and 90% values continue to be some of the lowest for our monitoring history. Copper numbers following the same trend line as the lead numbers. And of note, in this year, in 2017, is the first time we did not have any samples exceed the 15 part per billion action level. Actually, our highest value that we saw this year was 11 parts per billion. Again, so we're very pleased where we stand right now with the lead and copper rule. So if there's any questions, I will stand by. And here's my email address if you want to talk to me further down the line, and my telephone number. Thank you.
Great. Thanks, Mike. Great presentation. I'm going to go ahead and show everyone There we go. Here's a look at our Carus Corporation contact information. So this is our North American Regional Sales Manager here by territory. At the bottom, you'll also see our general Carus contact information. So if you think of any questions while I'm finishing up here, go ahead and type those into the questions section. If you would like a copy of the PDF, then please get in touch with me and I will get you a copy of that. Also, this has been recorded and we'll send out the link to all the attendees. And there are a couple questions. So one for you, Mike. So the public communications that Racine was required to send out, did you get those recommendations from other sources such as the AWWA, or is that something that you guys drafted internally?
Basically, we had some input with an engineering consultant that we'd hired. So I think we brought together information from a lot of different sources. So it wasn't strictly something that we thought of ourselves. So AWWA was probably part of it, but there was probably other sources also out there. And well, of course, they're trying to follow the regulations. So as far as what's included in the language, which looking at the in our cases, the Wisconsin Department of Natural Resources had to follow what they have as required language in the document that you're sending out.
Okay, great. And then a question for Darren. What would be the typical feed rate, which is resulting in the phosphorus concentration in wastewater with an effluent limit of 0.075?
So when we talked about dosages in the presentation, there's a difference between phosphate as PO4 and phosphorus as P. So a typical dosage, like I talked about in the presentation, of 1 milligram per liter as total phosphate, which would be as PO4, would actually give you a milligram per liter reading of 0.33 milligrams per liter as P. So when you think of that dosage as 1, you think that would affect your wastewater as 1 part, but it's actually you need to divide by 3 to get to the level as phosphorus of 0.33. In the case of wastewater, you're adding to what will go to the wastewater plant, so you would be adding 0.33 as phosphorus to the wastewater, but it's really at the wastewater plant what type of removal process they have that affects the lower limit that they get to. In this case, they're saying their effluent limit is 0.075, and what you would say is, well, you're adding 0.33, you're obviously above the 0.075, but typically a wastewater plant's going to see 4 to 8 milligrams per liter, depending on their waste sources, of P prior to you adding that 0.33 on. So it's just a small amount compared to the total amount that the wastewater plant typically sees. And it's really going to be whether they have a biological process, whether they have filtration at the back of their plant, whether they're doing some kind of chemical precipitation with alum or iron salts. Those are really what's going to determine if you get into compliance with that wastewater effluent level, because you already see quite a bit of phosphorus at the wastewater plant that's not from the drinking water side.
If I could add to that, Darren, when the LCR revisions were first being talked about and what they may require, what we've heard is that the EPA wants to have more phosphorus added or phosphates added to the drinking water for better corrosion control, which is obviously going to have a direct effect and the opposite of what wastewater people want to see. I talked to the Racine wastewater superintendent. He went back and looked at his information, and over the course of 1990s, when we first started adding phosphate to the water, their loading rate of phosphorus to the wastewater plant has been decreasing, not increasing. Now that probably has a lot to do with industry moving out of our area here in the upper Midwest, but they did not see, as we added more phosphates to the water, they saw a decrease in phosphorus coming into the plant. Now, obviously, it might not hold true across the country, but what we see here in Racine is less phosphorus in our wastewater plant.
No, that's a great point.
Yeah, thanks, Mike. Yeah, one of the things that also affects that, like you mentioned, industry, there's been a switch from the consumer side. A lot of our cleaners and detergents don't contain as much phosphate, and typically those things were 1,000, 10,000 parts per million of phosphorus that they would be adding when you did a load of laundry or cleaned your dishes. So as we remove those from different products that consumers would use, and then an industry changes what they use as well, that's all kind of overall shifted the numbers down as well. Yeah.
Great. Well, again, thank you, Darren and Mike, for presenting. Thanks for everyone for attending. If you think of any questions after we conclude here, please get in touch with Carus, and we can put you in touch with either Darren or Mike. And if you want to join any of our future webinars, check out our website, and you can register from there. Thanks, everybody.